So welcome to my channel on technology space with machine learning and artificial intelligence. So I am starting the main topic of the second playlist of maritime technology from this video. So the today's topic is apparent center of gravity in ships. So this is the part one of a two-part series. So let's elaborate why this concept of apparent center of gravity is an important concept for the shipping industrial applications. So the main reason is when we are applying dynamic or kinematic equations into ship motions, the mass, weight, inertia, and the position of the center of gravity will determine how such equations should be used. So since vessels are navigating in ocean environment where these vessels often can encounter harsh weather conditions or the environmental conditions, the respective mass, weight, inertia, and the center of gravity can vary. This is also can vary due to the vessel load conditions. So in this presentation, we are focusing on the concept of this variation in the center of gravity. So that because of that variation, we are introducing this new concept called apparent center of gravity to represent the variations in the actual center of gravity in these ocean-going vessels. However, we will start from the scratch to explain how this variation on the center of gravity can occur. So let's start from the scratch by describing what is a rigid body. Because at the end of the presentation, we would compare this rigid body into a ocean-going vessel. So the rigid body is an idealization of an object that does not change or deform its shape. So because of that reason, the mass distribution in this rigid body is fixed. So the mass can be defined as a measure of the amount of matter in an object. So as you may have noted, that mass in this rigid body I have denoted by m. So if you hold this rigid body against the gravitational field by a scale, so the scale reading should show the total weight of the rigid body. So the total weight of the rigid body is defined in this case as W, which is equal to the mass of that rigid body, which is m times the gravitational constant. And you should also note that I have denoted that volume for that rigid body as V, and the mass of that rigid body as m, and the density of that rigid body as rho in this situation. So let's try to define the concept of the center of gravity of this rigid body. So the center of gravity can be defined as the average location of the weight of an object. As you can see, the center of gravity is denoted by Cg in this figure. Therefore, the weight force is applying downwards from that specific point. Since the mass distribution is fixed in this rigid body, the center of gravity also fixed for that rigid body. So let's try to go through some parameter relationships on the mass, volume, density, and the weight in this rigid body. I know this equation somewhat simpler, but for the sake of the clarity in this presentation, I would go through these parameter relationships. So the density of this rigid body can be written as the mass divided by the volume. So the density can be defined as the mass per unit volume. And then if you multiply both sides of that equation by the volume of the rigid body, you will end up with density times the volume of that rigid body equal to the mass of that rigid body. So if you flip the previous equation, you will end up with the equation saying the mass equal to the density times the volume of that rigid body. And as you know, the weight we defined as the mass times the gravitational constant in this situation. So then you can apply that mass equation we have derived previously into this weight equation we have derived in the previous equation. So then you will end up with the equation says the total weight of that rigid body equal to the density times the volume of that rigid body times the gravitational constant. So let's try to understand what could happen to a rigid body when it's partially submerged in a specific fluid. We made several assumptions with respect to the fluid. So here we are assuming incompressible fluid in a static conditions. For example, water can be an approximation for such type of a fluid. And the fluid density is defined as rho F in this figure. And you may have noted the boundaries of that fluid tank is represented by dashed lines. So that means this is a larger tank with compared to its boundaries. So the main assumptions I am going to introduce in this situation because of these boundaries would be when you submerge a rigid body into that tank, the variation in the fluid level is somewhat negligible. So when you submerge that rigid body into this fluid tank, the first thing could happen is the buoyancy will work against the rigid body. That means a buoyant force will act against the rigid body at the center of gravity of the fluid mass. So the center of gravity of the fluid mass is represented by CGF. So the buoyant force is equal to the density of the fluid times that submerged volume of that fluid times the gravitational constant. So the difference between the weight coming down from the rigid body as well as the buoyant force working against the rigid body will be reflected on the scale reading. So because of that reason, the scale reading would be W minus U. Due to the buoyant force acting upon the rigid body from that fluid, the rigid body feels like it has lost some weight. So that concept is reflected on the scale reading, saying it is the reading of W minus U rather than the W. So that means the scale is telling that initial weight of the rigid body is somewhat reduced due to that buoyant force. So that means the rigid body will feel like it has lost some weight. So since it has lost some weight, the mass distribution in that rigid body should also be changed. And then this concept is introduced in this case as the reduced mass. So if the reduced mass going to be a part of that new rigid body, so then it should have a new weight value also. From the previous scale reading, it would the new weight value of Wn equal to the W minus U. So since the reduced mass concept for this rigid body is introduced due to this buoyant force, the mass distribution in this rigid body has also changed. So since the mass distribution has changed, its center of gravity should also be changed. So the initial center of gravity for this rigid body was in CG location. Now you can see that center of gravity has shifted upwards in this rigid body, and it is denoted by CGA, which is defined as the apparent center of gravity for that rigid body. So you can imagine in this situation, since the mass distribution has changed, especially you lost some mass in this rigid body, so the center of gravity location has changed. So that variation being introduced as the apparent center of gravity in this presentation. So let's go through some parameter relationships for this new rigid body, which is the original rigid body with the reduced mass. So initially, let's say that weight of that rigid body equal to the new mass of that rigid body times the gravitational constant, which is reflected by mn times g. That's also equal to the original weight of the rigid body minus the buoyant force, which is W minus U. So if we divide the previous equation, it's both sides by the gravitational constant, you end up with a new equation saying the new mass of this rigid body equal to the weight of the rigid body minus the buoyant force divided by the gravitational constant. You should remember the weight of this rigid body is the original weight of that rigid body itself. So then you can say something about the density of that material in this rigid body, which is equal to the new mass of that rigid body divided by the new volume of that rigid body. So the new volume can be reflected by the original volume of the rigid body minus the reduced volume of that rigid body. So if you multiply the both sides of the previous equation by Vn over rho, you will end up with a new equation saying Vn equal to the mass of the new mass of the rigid body divided by the density. And then if you apply that mass equation which you have derived in the previous steps into the previous equation, so you will end up with a new equation is saying that new volume of that rigid body equal to the original weight of that rigid body minus the buoyant force divided by the density times the gravitational constant. So that means W minus U divided by rho G. So since you have this new volume of that rigid body, you can apply into the this new equation, which is reflecting the weight of that new weight of this rigid body equal to the density times the new volume of that rigid body times the gravitational constant. So the new volume of that rigid body can be calculated from the previous equation that we have derived. So let's recap what we have discussed so far. We had the original rigid body and then it was submerged into a specific fluid. So due to that submerged volume, there was a buoyant force working against the rigid body. So because of that reason, the rigid body felt like it has lost some weight. So due to the same reason, we said that the mass on that rigid body has reduced as this reduced mass. So due to that same reason, the center of gravity of that rigid body has shifted upwards, or it was moving away from the reduced mass. So think about a situation if you're adding additional mass into the existing rigid body. So here we are trying to compare when you add a mass into the rigid body as added mass, what you could happen into the rigid body. Of course, obviously its weight will increase in this situation. So due to the added mass conditions, which is the added mass is reflected by dm in this figure, you will have additional weight. So the added weight is reflected by dw, and then which is equal to the dm times the gravitational constant. So due to the same reason, the new weight of the rigid body is reflected by Wn in this situation, and which is equal to W plus this dW, which is this added weight of this rigid body. And this value should also be reflected on the scale reading. So let's try to summarize that we have discussed on this scale reading of the rigid body. There were two situations we have discussed in this presentation. The first one, when a rigid body is submerged into a fluid, it feels like it has reduced mass due to this buoyant force. That was reflected on the scale reading, saying scale reading is equal to its original weight minus the buoyant force. So this is where the reduced mass concept was introduced. So due to the same reason, the center of gravity of that rigid body is moved away from the reduced mass. In this case, it was shifted upwards in this figure. And then the second case, we have introduced the added mass into this rigid body. Due to the same reason, the weight of that rigid body has increased. So the center of gravity also changed. It is more the center of gravity is moved towards the added mass in this situation because due to this mass distribution change in this rigid body. So the same variation is reflected on the scale reading. It is showing that the new weight of the rigid body equal to its original weight plus the new added weight into this rigid body. So I have mentioned that the center of gravity of this rigid body has shifted downwards due to that added mass. So this is kind of point we can also discuss the center of gravity variation due to this added mass as well as the reduced mass. You can imagine in the reduced mass situation, the center of gravity has shifted away from the reduced mass. In the added mass case, the center of gravity is moved towards the added mass. So when these rigid bodies are interacting with fluids, you can imagine these center of gravity locations can vary. I think the reduced mass situations we have discussed, saying when a rigid body is submerged into a fluid, then you would see this reduced mass situation. The added mass situation I would discuss in my future slides. Since here we are discussing the fluids, the rigid body interactions with fluids, you can imagine vessels can be approximated towards the rigid body, and then the fluid can be the ocean environment where these vessels are interacting. So due to that same reason, I think you can imagine that now we are coming towards explaining the actual center of gravity of these vessels, how it can vary when these vessels are interacting with the ocean environment. So because of that same reason, we are introducing this new concept called apparent center of gravity. So that means even though a rigid body has a fixed center of gravity itself, when these rigid bodies are interacting with fluids, it could have this center of gravity being changed due to this interaction. So the new concept of apparent center of gravity is used in such situation. And this is what I'm going to discuss throughout this maritime technology playlist series in the future. So that's the end of this video. Hopefully you have enjoyed that. So if you're still interested, please stick around. Thank you.